All right, well, we'll go ahead and get going. So we've taken the fatty acid and we've prepped it for beta oxidation by first activating as the AMP, the fatty acyl AMP, and then doing nucleophilic acyl substitution with the coenzyme A thiol to give you a thioester. Thioesters are great because they're pretty reactive, but they're also kinetically stable. So they can last quite a long time, but they still do acyl substitution chemistry really easily, and it's a convenient sort of placeholder for a really good leaving group. So our goal in fatty acid beta oxidation, and I'm just going to draw, say, a 16 carbon, 2, 4, 6, 8, 10, 12, 14, 16, a 16 carbon fatty acid thioester. Our goal is to do chemistry that allows us to break off individual 2 carbon units, but to do so in a way that's totally iterative so we can use the same enzymes for all of it. And you're going to see how the steps here are iterative. The reason we're calling it beta oxidation has to do with our traditional way of naming the atoms of a carbonyl. The one that's adjacent to the carbonyl carbon is alpha. The one that's adjacent to alpha is beta. So we're going to oxidize the beta carbon, and our goal is really going to be to break the bond between alpha and beta carbons. And we want, after that bond is broken, we want the beta carbon to be the new carbonyl carbon. If that's sounding familiar and you're thinking aldol or Claisen chemistry, you're on the right track. These are reactions, at least the retroaldol and the retroclaisen are reactions we've used to break the bond between alpha and beta carbons of a carbonyl. But first we've got to set up to do that, because as you're looking right now, the beta carbon just has hydrogens on it. There's nothing there to indicate that this could have been an aldol product or a Claisen product. All right, so I'm just going to show you, we're just going to use ours, and I'm just going to show you the first two carbon units of this fatty acid. And then I'm going to abbreviate the coenzyme A thiol. The first reaction is an oxidation reaction, and it's going to convert this fatty acid into an alpha beta unsaturated carbonyl compound. So it's going to introduce a double bond between the alpha and the beta carbons. And you can see, if your goal was to break the bond between the alpha and the beta carbons, you can sort of see how it might be a good idea to introduce a double bond there, because suddenly that looks like an aldol product, that alpha beta unsaturated carbonyl compound. This is an oxidation reaction. If you look at what's missing, we've lost H2, we've lost a carbon hydrogen bond on the alpha carbon, and we've lost a carbon hydrogen bond on the beta carbon. So the enzyme that catalyzes this is called dehydrogenase. It's called acyl-CoA. That describes the substrate, acyl group, and CoA, dehydrogenase. And the cofactor that does this is not NADH, but it's a new one called FAD. And both hydrogens end up on, both hydrogens, one from the beta carbon and one from the alpha carbon, end up formally on FADH2. So I'll show you what FADH2 looks like. It's not going to be as easy to understand as NADH and NAD+, so you may have to just accept on faith that what I will show you is mechanistically reasonable. To begin with, though, the first step of the reaction, even before I show you the structure of FADH2, this reaction proceeds, at least in the first step, by deprotonation of the alpha carbon by the enzyme to make an enolate. So we're going to remove that alpha proton. And then here's the structure of that enolate with a negatively charged alpha carbon. All right, and if this were an aldol reaction and we had a leaving group on the beta carbon, what we would have just done would have been like an E1CB reaction mechanism. We remove the proton first, and then this negative charge could kick down and a leaving group could leave. The only problem is H- is not a good leaving group. But as we saw earlier, if you have the right hydride acceptor nearby, it'll work out okay, because H- doesn't actually leave, it's handed off directly to something that can receive the H-. What we need is an oxidizing agent. So this is where FAD enters in. FAD stands for flavin adenine dinucleotide. It's really similar to NAD+, only the warhead, or the thing that's attached to the anomeric carbon of ribose, is different. So I'm going to show you just a portion of what FAD is. I'm going to try not to get it wrong because I always sort of forget what it looks like. All right, so this portion is C1 of ribose, and there's other parts of the molecule that I'm not showing you. Just go look it up on Wikipedia if you want to see what the structure is. My notes are tiny here, so I may have to get my old guy glasses out in order to see. I think we're doing okay. Okay, so that's a much larger group than NAD+. But we're going to see that it is electrophilic here. So hydride is going to attack there, and then a proton, hydride is going to be delivered to that nitrogen, the pink nitrogen. And then we're going to need to pick up a proton on the orange nitrogen. And then, yeah, that R group is just the C1 carbon 1 of a ribose ring. Okay, so electrons on the alpha carbon will kick down to form a new bond between alpha and beta carbons. At the same time, that hydride is delivered to the pink carbon of FAD. You can see that the pink and the orange nitrogens are conjugated to each other. And so we can push arrows this way, showing the proton being delivered or being picked up on the orange nitrogen, like this. That gives you the new double bond shown here in red, this new bond between alpha and beta carbons. And then I'll draw for you the reduced form of FAD when we've added the hydride to the pink nitrogen and then a proton to the orange nitrogen. So that's our H2 carried away with FADH2. This is a redox reaction. You can tell it is because it's a dehydrogenase enzyme. This fatty acid is the reduced form, and it gets oxidized to the alpha beta unsaturated carbonyl compound. The FAD is the oxidized form, and it gets reduced to form FADH2. FADH2, you might ask, why is nature choosing to use FADH2 here versus NADH? NAD, or rather FAD, to do the why is it nature using FAD to oxidize the fatty acyl thioester rather than NAD+? It turns out NAD+ and FAD have different oxidation potentials. That means the redox reaction where FAD gets reduced to FADH2 versus NAD+ being reduced to NADH have different thermodynamic favorability, and so you need to match that with how favorable the other part of the reaction is. The other thing you will learn in biochemistry is that FADH2 and NAD+ enter the electron transport chain at distinct places, and so FADH2 is a little bit less energy rich. It generates fewer molecules of ATP than does NADH. All right, so with the fatty acid thioester now oxidized to the alpha beta unsaturated carbonyl compound, the next step is conjugate addition. So far, it's going to look like we're setting ourselves up to do a retroaldol reaction, because we're going to start with the alpha beta unsaturated carbonyl compound, and we're going to do conjugate addition of water at the beta carbon to get a beta hydroxy carbonyl compound. The mechanism of this reaction is basically going to be exactly what you would expect. You need to remove a proton from water, then water is going to attack the beta carbon via conjugate addition. That's going to give us a negatively charged intermediate with a negative charge on the alpha carbon. Here is the OH group that just ended up now on the beta carbon. Here's the negatively charged alpha carbon enolate, which is then going to pick up a proton from the enzyme or from water, and the product is going to be the beta hydroxy carbonyl compound shown here. All right. And now you're starting to see why this is called fatty acid beta oxidation, because we've added an oxygen. The net effect of these first two reactions is to add an oxygen to the beta carbon of our fatty acid. Now, if you're looking at that, that product is a beta hydroxy carbonyl compound. You could be forgiven for thinking, hey, let's do a retroaldol reaction. So let's just talk about that. What if we did a retroaldol reaction? This portion would be the enolate. This portion would be what kind of functional group? Right, you can tell it would have been an aldehyde because there's a carbon-hydrogen bond there, right? Remember that our goal is not only, and that would accomplish one of our goals, which is to clip off a 2-carbon unit that we can use as acetyl-CoA in the citric acid cycle. But over here, we'd be left with an aldehyde. And if you recall, our first step was on a thioester. Ideally, after we clip off that 2-carbon unit, we want what's over here to be a thioester as well, so we don't have to invent new enzyme machinery to do subsequent steps. We want this process to be iterative. So instead of just forging ahead with the retroaldol, nature gets creative, and that's, let's not do a retroaldol, let's do a retroclason. So the third step of fatty acid beta oxidation is going to be another oxidation step. We're going to oxidize the beta hydroxy group to a beta keto thioester. And remember, every time we're doing an oxidation step and we generate FADH2 or NADH, that's ATP, that can be converted to ATP in the electron transport chain. So what we're going to do now starts with the beta hydroxycarbonyl compound. The enzyme that catalyzes this reaction is called a dehydrogenase. I'm not going to draw the mechanism for this because it involves an NAD+ based oxidation, which you have already seen. Basically, you can expect that what's going to happen is a base is going to remove the proton from the alcohol on the beta carbon. Electrons are going to kick down, and hydride is going to be delivered to NAD+, just like we saw earlier. But now we've got a beta keto thioester, and we're now all set up for a retroclason. Okay, now we're set up to break the bond between alpha and beta carbons. And just to remind you, what is a Claisen reaction? In the Claisen reaction, we take two molecules, in this case of the same ester. We make one of them an enolate. We make a new bond between alpha and beta carbons. We get a tetrahedral intermediate. And then the leaving group leaves to give you a beta keto ester. What is a retroclason? Well, that would simply involve the nucleophile attacking the beta carbon to give you a tetrahedral intermediate. All right, so let's show you that retroclason step from fatty acid beta oxidation. Here's the beta keto thioester. I'm going to again highlight the 2 carbon units. And the effect of this reaction is going to take, this will involve another equivalent of coenzyme A. But when we're done with this reaction, you'll see that the purple 2 carbon unit has been broken off first as an enolate and then picks up a proton to just become this 2 carbon acetyl-CoA. And then we now have, this, we started out with what I called our 16 carbon thioester. At the end of this, it's now a 14 carbon thioester. And this can go back to step 1 of fatty acid beta oxidation and go around again. And so successively, nature's going to clip off these individual 2 carbon pieces until we're down to the last 2 carbons. How does this process happen? Exactly the way you would expect for a retroclason. The enzyme residues that are involved in this process are known. Should I show you the whole thing, or should we just summarize it and move on? I'm tempted. Summarize, you just don't want to know. Okay. I know you don't want to know, but if I oversimplify, then dang it. Okay, well. Nope, we got to do the whole thing. Because if I show you overly simplistically, it's actually not true. And so I want to show you what nature's actually doing. So, and why does nature do it this way instead of an overly simplistic way? I don't know. Someday when you're in the celestial kingdom and taking your world building biochemistry lessons, you can ask why it didn't work out that way. I got nothing at this time. I'll be there in the class asking the same question too. I once had a biochem professor that was like, you know, you just as well put in your time and learn this stuff now, because if you don't, you and I are going to be there and I'm going to be teaching the class. And I thought, yeah, right, like you're even going to be there. Just kidding. He was a really good professor. I liked him. But if you've read Dante's Inferno, there's a special corner of hell reserved for OChem professors. All right, so it turns out that nature uses thiol-bearing side chains inside the enzyme to do a lot of the claisen chemistry. And the coenzyme A thiol only comes in a little bit later. So a histidine side chain removes a proton from a cysteine side chain, which attacks the beta carbon as a nucleophile to give you a tetrahedral intermediate, which we're going to draw like this. So here's the negatively charged oxygen. Here's cysteine 125. That's the sulfur residue. And then here is the remaining portion of our molecule. Here's the 2 carbons that are eventually going to come off as acetyl-CoA. And that happens at this stage, actually. The electrons kick down and the leaving group leaves. The alpha carbon on that enolate leaving group, actually there's evidence that it picks up a proton from another nearby cysteine side chain as the leaving group is leaving. This is cysteine 403. And again, you're seeing residues that are very far apart in primary sequence are all located in the active site, telling you that the whole point of a lot of enzyme tertiary structure is just to bring the key players together. So that's the stage at which we lose acetyl-CoA. That now can diffuse away and get taken to the citric acid cycle. Now we have an enzyme-bound thioester. This is still cysteine 125. And the negatively charged cysteine 403 is the thing that appears to do the deprotonating of the coenzyme A thiol. Then that attacks to give you a tetrahedral intermediate. So all of this really is now just nucleophilic acyl substitution chemistry. And then electrons are going to kick down and kick off the enzyme-linked thiol, which as it's leaving is going to pick up a proton from our old friend histidine 375 that you forgot about. This was the one that did the deprotonating of cysteine 125 to begin with. And that's going to return the enzyme to its starting state where it can accept another molecule of substrate and go again. Oops, I like that color. So here is now our truncated 14 carbon fatty acid thioester and our 2 carbon acetyl-CoA, which can then go to the citric acid cycle. Okay, questions about that? I hesitated to show you all this because I know when I show you detail, I know at least one of you and more of you are like, do I need to memorize all of that? And I'm like, no, because I don't have it memorized, but you should understand the chemistry so that, and really what you're seeing here is no different than anything you've seen on a previous exam of mine involving nucleophilic acyl substitution steps, okay? So understand the logic of what's going on, and with fatty acid beta oxidation, you should understand why it is that we need to start by putting the double bond here between the alpha and the beta carbons so that we can get the oxygen there via conjugate addition, so we can oxidize to get the beta keto thioester so that we're set up for this key retroclason reaction. And notice the beauty of the process that clips off acetyl-CoA and leaves behind a coenzyme A thioester that can go right back to step 1, and then we just circle around until we've chewed up that fatty acid into individual 2 carbon units. All right, lipids. So now carbs. Let's do glycolysis and metabolism of carbohydrates from glycolysis to pyruvate, and then we'll go to the citric acid cycle. Any other questions about fatty acid metabolism? All right, so glycolysis involves, get ready for this, 10, I think it's 10 reactions. And we'll learn the mechanisms of all of them, though some of them you've already seen because they're going to involve kinase or dehydrogenase steps that you've already worked on. Let me give you the overview of glycolysis. Glycolysis is going to take glucose, which is C6H12O6, and then convert it into 2 molecules of pyruvate, which is C3H4O3, and I'll draw that here. And then along the way, we're going to convert 2 ADPs and just a phosphate group into 2 molecules of ATP. So that's sort of payoff. We're also going to take 2 molecules of NAD plus and convert them through dehydrogenase oxidation type chemistry into 2 molecules of NADH, and then just to balance out the charge, we're going to have to remove overall 2 protons. Glycolysis is what's known as anaerobic respiration. This doesn't involve the electron transport chain, and this takes place in the cytosol. Glycolysis has 2 phases. The first is an investment phase, and the second is a payoff phase. In the investment phase, we're going to end up consuming a couple molecules of ATP in order to set up the chemistry the way we want. You're going to want to pay attention to where the good leaving groups are, and you're going to want to pay attention to setting up glucose so that it can break apart into 2 equal portions via a retroaldol reaction. We'll talk about what the molecules are called. We'll talk about what the enzymes are called. I'll also point out which steps are irreversible, that is so downhill in energy they can't go backwards. That's important in biochemistry because it's those irreversible steps that are the gatekeepers for these reactions. Once you commit, it's like Yoda said, once you start down the dark path, forever will it dominate your destiny. It's a really pessimistic view of humanity, isn't it? What about repentance, Yoda? But in that way, when you go through steps in chemistry that are irreversible, you've committed the molecule of glucose already. And so those steps are tightly regulated to keep everything in balance. All right. So step one of glycolysis is in the investment phase. Step one is irreversible, so you don't go backwards from this. There's other enzymes that deal with the backwards reaction. The starting material is just glucose, which we're going to draw in its cyclic hemiacetal form, though just as shorthand, I'm going to continue to call this glucose, even though it should be called D-glucopyranose. We're not really caring about whether or not this is the alpha or the beta anomer. Those are in equilibrium with each other in aqueous solution, as I showed you in one of the video lectures from last week. This is a kinase reaction. It's catalyzed by an enzyme called hexokinase. Hexo is for hexose, a 6-carbon sugar. And kinase is going to refer to transfer of the gamma phosphate group from ATP to this carbon 6 hydroxyl group of glucose. So 1, 2, 3, 4, 5, and 6. It's that hydroxyl group that's outside the ring that is going to get the phosphate group. The product now converts glucose with the C6 hydroxyl group into the C6 phosphoester. So this new bond between oxygen on carbon 6 and phosphorus is called a phosphoester. This is downhill in energy. It involves conversion of ATP to ADP, and it's the gamma phosphate group of ATP that gets transferred. I'm not going to draw the structure of ATP for you. You can look that up in your notes earlier, though I'll point out that the bond between the gamma and beta phosphate groups is called a phosphoanhydride, whereas the bond between oxygen on C6 and the phosphorus there is called a phosphoester. And in the same way that we learned, as we were learning about nucleophilic acyl substitution, that esters are more stable than anhydrides, so phosphoesters are more stable than phosphoanhydrides. So the free energy for this reaction is downhill. I don't want you to memorize this number, though you do need to know that this first step is irreversible. But the reason it's irreversible is because the phosphoester is so much more stable than the phosphoanhydride. And the product here is called glucose 6-phosphate. All right, and the mechanism of that is just what we would talk about, what we had seen previously. You got to deprotonate the C6 hydroxyl, then that attacks the gamma phosphate group. You get a pentavalent intermediate, and then the electrons kick down and ADP leaves. So C above for the mechanism. Go ahead.
Do you just use a base to deprotonate?
Yeah, you'd need some base, probably from the enzyme. Yep, others? Okay. The next reaction is a little bit more interesting than the kinase reaction. The starting material is, of course, glucose 6-phosphate, but the enzyme is called glucose 6-phosphate isomerase. And the reaction isomerizes glucose 6-phosphate into fructose 6-phosphate. A lot of F's and pH sounds there. Let me draw fructose 6-phosphate for you, and then we'll talk about the mechanism of the reaction. I think you've seen fructose before in a practice problem or perhaps on an exam, I'm not sure. Here is carbon 6, 5, 4, 3, 2, and 1. I need to draw an up OH group on carbon 3. Notice that fructose is a 5-membered ring containing sugar. Let's focus in on the hemiacetal carbon of glucose 6-phosphate. That's the one that's attached to an OH group and an OR group. Just for clarity's sake, I'm going to draw in, I'll draw like the beta anomer because I want to draw in the carbon-hydrogen bond that's present. Because I need you to see the difference between glucose 6-phosphate and fructose 6-phosphate, focusing in on that anomeric carbon. In its open chain form, glucose would be an aldehyde. You see that that anomeric carbon is bonded to an OR, an OH, and an H. Okay, in its open chain form, glucose is an aldehyde. That's why we call it an aldose. In its open chain form, look at the difference with fructose. The anomeric carbon is carbon 2. Here's an OH, there's the OR group. The other two are carbons. So fructose 6-phosphate is a ketose, meaning in its open chain form, it would be a ketone, all right? So let's talk about the mechanism of this reaction. I'm going to gloss over some of this because some of this is stuff you've seen before, and I think you can find it by looking in your notes or consulting previous chapters. So I'm not going to show you the opening of a 6-membered ring hemiacetal. Presumably you can use that. You can do that. You could use groups from the enzyme or just general base and acid groups to catalyze that process. I'm going to draw you the open chain form of glucose 6-phosphate with the aldehyde on carbon 1. Now I'm also, and because I'm glossing over that, I'm going to use an equilibrium arrow because you already know that that process is an equilibrium. I'm going to scoot this down over the page divider because I know when you render this as PDF, if you span a page, it's kind of funny. I'm also going to draw for you the open chain form of fructose 6-phosphate. I'm calling that ring closing because in the forward direction, making the closed ring, it would be a ring closing reaction. We'll do this just by copying this structure. Okay, the C5 group becomes a hydroxyl, and carbon 2, the anomeric carbon, becomes a ketone. So we need to somehow connect the dots from this aldehyde to this ketone. And you might look at that and say, well, it looks like we need to reduce the aldehyde and then to an alcohol and then oxidize the C2OH group to a ketone. That's a decent strategy and a decent hypothesis, but actually nature doesn't need to do that. You can do this without redox chemistry at all You just do it through proton transfer, 2 successive, basically tautomerization steps. So, notice that carbon 2, and I'm going to draw the alpha proton on carbon 2. Notice that carbon 2 is alpha to a carbonyl. So we can use a base to remove the proton on the alpha carbon to get the conjugate base enolate, which I will draw here. Okay, that's the enolate. I've simply drawn the resonance structure where the negative charge is on the carbonyl oxygen instead of on the alpha carbon. Then the carbonyl oxygen, the oxygen of the enolate, is going to pick up a proton on to give me an enol. And this intermediate is a key one. It's called an enediol intermediate. These 2 steps from deprotonating the alpha carbon to the enediol, you've seen stuff like that before. That's tautomerization. We've gone from an aldehyde to an enol form. But the point of this enediol is that it's an enol in 2 directions. Here is an OH and here's a double bond, but here's an OH and there's a double bond. And that enediol allows you to switch easily between glucose and fructose, because once you're at the enediol, which one's the carbonyl carbon and which one's the alpha carbon? It could go either way. I could tautomerize back to the aldehyde, or I could tautomerize forward to the ketone. Going forward, you can push arrows in a couple of different ways that give you sort of equivalent resonance structures. I'm going to have electrons on the C2 hydroxyl kick down to form a carbon-oxygen pi bond. At the same time, I'm going to break the bond between C1 and C2. Oops. Once I make that new pi bond, C2 becomes once I make the new carbon-oxygen pi bond, C2 becomes my carbonyl carbon and C1 becomes my alpha carbon. I'm going to pick up a proton from some acid, perhaps an enzyme side chain, perhaps water. That's going to lead to the following intermediate, where you will see that we have established the new carbon-oxygen pi bond with C2, our new carbonyl carbon. And we just picked up a proton on our alpha carbon. Then I just need a base, perhaps the conjugate base of the acid, perhaps some side chain group to remove a proton from that C2 carbonyl oxygen, and that will get me to the open chain form of fructose. Alternatively, the tautomerizing from the enediol back to this keto form, I might have deprotonated that oxygen and then had electrons kick down and pick up a proton on the C1. The order of the proton transfer steps here doesn't really matter. Okay? Questions about that? Yeah?
All of that is reversible.
All of that's reversible, yep. The free energy for that reaction, you would predict the aldehyde to be a little less stable than the ketone, but the delta G for this reaction is pretty close to zero, meaning, yeah, totally reversible. Other questions? Yeah?
The base that deprotonates in the last step, could that just be the conjugate base of the acid?
Yep, could be the conjugate base of the acid, could be the same enzyme side chain. I don't know what it is. It may be known, but yeah. Okay. So the third step, which we're not going to show you the mechanism of because it's simply a kinase step, is going to be to take fructose 6-phosphate and we're going to invest one more molecule of ATP. We're going to again transfer the gamma phosphate group from ATP, but this time we're going to transfer it to the C1 hydroxyl to give what's called fructose 1,6 bisphosphate. The 1,6 tells you where the two phosphates are. The bis tells you that there are two phosphate groups. What's the difference between bisphosphate and diphosphate? I'm not really sure I know. The enzyme that catalyzes this is, let's see, I'm going to get this wrong. No, is called phosphofructokinase because you take phosphofructose or fructose 6-phosphate and you do a kinase reaction on it. This step is also irreversible. Again, it replaces a phosphoanhydride in ATP with a more stable phosphoester. I'll just put a number on it so you can see how irreversible it is. At room temperature and in cells, delta G of minus 1.4 kcals per mole is an equilibrium constant of 10. So that size delta G is an equilibrium constant of about 1,000. And so it's definitely another irreversible step. And this sort of concludes the investment phase of glycolysis. In the future, we're going to now be generating sort of molecules that we can use to get ATP. All right, that's a good enough place to pause. So next time we'll finish up glycolysis and then we'll talk about the citric acid cycle. We probably won't finish all of metabolism next time. We'll probably need to bleed into Wednesday a little bit. All right, have a good weekend. I will see you Monday.